Hi everybody, I'm Matt Topol, and yeah, this is JSON Intel. Going to talk about the recent, the variant type that was added to Parquet, Iceberg, and also Apache Arrow too. First, just a little bit about me. I am co-founder of a startup columnar focused on data connectivity, specifically with Apache Arrow and ADBC. And if you want to know about ADBC, catch me on a talk later on this afternoon because I have another one where I'll talk about ADBC. I'm PMC member of Arrow and on Iceberg, and I wrote on Arrow in memory analytics with Apache Arrow. So that's a bit about me and why you should care at all what I'm saying. But for now, let's talk a little bit about storing data in warehouses. I can't do show of hands like I would normally do in a talk, but I guess put it in the chat. How many people store JSON data as just strings in your databases, in your data warehouse? Like, this is a common thing, and many of us do this, and we just go, this is fine. Just store the raw JSON into the database as is in my data warehouse, in my lake house, wherever. Because, well, we, haven't learned after so many years of doing this stuff. Because actually interacting with those JSON strings is awful. And so this is kind of where some of this comes from. So dealing with semi-structured data is the real place where you don't really have a static schema. Someone in the chat mentioned they use the variant in Snowflake. Well, yes, that is the purpose of this variant type that we created. Unfortunately, Snowflake still returns variant as a string if you query it rather than actually giving you this variant type, but we'll get to that. So, in general, how do we end up representing this semi-structured data? As we mentioned, lots of people will just store JSON as strings, which is, your data is no longer column-oriented. You're sacrificing your performance to not have to deal with changes in your structure and your data and your schemas. Another possible thing that people do is schema inference, where you just kind of figure out the schema on the fly as you go, which works great until it doesn't. Another fun one that is common is also we flatten everything. You have your semi-structured data and you just flatten all of the stuff into these scenarios, which now you have this explosion of fields and schema anymore, and your data engineers hate you. And the last one that's common is also just using NoSQL, which is kind of just running away from the problem of the semi-structured scenario, and you just get different problems when you do that. You're working with it's just an entirely different scenario of problems you have to deal with because you're sacrificing all the benefits of this column-oriented structure and all the performance benefits of analytics just to not have to deal with schema weirdness. And so that's where this variant type came out of. But all this discussion here of, well, we have structured data. We want to have semi-structured data. Why not both? And so the variant type that was added for Spark and then Iceberg and whole nine yards, it's a great example of a whole bunch of communities coming together and ecosystems all working together for this benefit. You get this hybrid storage model. It's using a binary format so that it's much more efficient than storing a raw JSON string, but it's also self-describing and embeds the schema so that you can easily adjust as necessary and figure it out on the fly. And then for those optimized scenarios of dealing with column-oriented data where you know that you're pulling individual fields that are always there, we have what's called shredding, which I'll get to. Now, the importance of the variant type is not just in the design, but it's this standardization. It's this creation of a standard way to represent, interact with, and utilize this kind of semi-structured data via the variant type. And so you end up with this. Actually, I need to update this slide because Parquet and Arrow extension types were finalized and exist. I need to update the slide. They are finalized, not almost finalized. But you end up where it's in Spark, Iceberg v3 edited to the Iceberg spec. Your schema can vary row to row because that's what variant types do. And in general, it's a superset of JSON. You can losslessly round trip JSON to and from variant as long as you don't care about the physical formatting like whitespace. And it gives you this efficient way of encoding data using binary representations for this variant style of data. And then you get this much more efficient way because we're going to dictionary encode the field names. So if you have a bunch of rows of the same fields, then you don't have to repeat the field names over and over again. And using offsets to manage the actual objects, which I'll show you the exact structure in just a second. The result here, as you can see by my little diagram there that I pulled from a Databricks blog post, is that interacting and utilizing the data interacting with just JSON-styled semi-structured data using this variant binary format was 8 times faster in their test cases, and I've seen it significantly faster or slower, but it's always significantly faster than just interacting with JSON as a string. Now, as someone in the chat previously mentioned, they used the variant type in Snowflake. I do not know what Snowflake's doing under the hood, but I know that they output it as a JSON string, which is not particularly useful. So what does this variant type actually look like? What makes it useful? So if we look at the actual variant type, on the left side of the slide here, we have a simple JSON array. Just a list with 2 objects that have the same field names. And so on the right, we can see how that translates. Now, you have a metadata that is going to, you have a metadata and you have a value. 2 separate buffers. 2 binary chunks. The metadata, as you can see, is a dictionary encoding of the field names. So there's a header that identifies, the version, the size, and so on. And then we have our dictionary. In the value, you have the actual array indication, where the first thing there is a binary, byte where the first couple bits identify it as an array type. It contains the length of the array, 2 objects. And then we have offsets that tell us where the actual values of the individual fields start. How do we get past the headers? First object 1 there, which gives us an object header, tells us the number of fields in the object, gives us field IDs, which are the ID of the dictionary, ID into the dictionary that tells us the key, the property name, followed by offsets that tell us where each value of the object starts. And then we have our string values. And then immediately following that, you have object 2. Same idea, header byte, number of fields, field ID, offsets, and so on and so forth. So you have this very structured way of representing semi-structured data. Now, of course, if you're familiar with Parquet, if you're familiar with Iceberg or Arrow, you might look and go, okay, but we already have a struct and list type. Why do we need this variant thing? And it's a valid point. You have structs, you have lists, you have maps, you have both. Why do we need yet another type? And the big difference is that structs and lists you must define all of the columns that are going to exist up front as part of the schema for those. Whereas the variant is flexible. For example, you can't do an arbitrary levels of nesting with a struct or a list because you need to up front know exactly how many levels. It also requires type consistency. If I make a struct or a list column, I have to say that, the field for, the type of the last name field is a string, which means that you can't actually have another one come in and have that be a list of strings. Or in the case on the right side, if I define a column as a list of floats, I can take nulls, but I can't throw a string in there. And so that's where this variant comes into play of real world data is messy. It doesn't always follow the type consistencies it should. And sometimes that's benefit, sometimes it's detriment. But in all cases, there's situations where you need to be able to handle these outliers. And using struct and list that are very, very rigid in their type definitions require knowing all of your possible fields up front is too rigid for this kind of semi-structured data use case. That's why variant makes sense, and that's why you use it over using those in this scenario. Now, for the supported types are everything you expect. It's like I said, it's a superset of JSON. In fact, it's better typed than using raw JSON. So if you were using JSON strings, using variants even better, not just because of the binary representation and the more consistency, but it's also going to give you a better type inference, type consistency, and rigidity in knowing what your types are. You don't have to parse a date string and hope it's the right date now. You can have a date type in your variant. Just like a date column, it's like a date column of the database. You have this extra layer of structure now. You have all the, these types. You have doubles, you have dates, you have timestamps, you have, whatever you need. And as I said, when we added it it was added to Spark, it was added to Iceberg, and the Iceberg community was like, we decided that because Parquet is such a connected piece of the storage layer for how Iceberg works, it was important that this variant type also make it into Parquet so that we don't have a mismatch between your table representation and your storage, and so that you can get that, zero copy representation where you don't need to manipulate the data that you read from Parquet to represent what Iceberg expects. And it's represented exactly as you'd expect. As I mentioned, there's a metadata and a value blob. Well, in Parquet, you have two leaf columns you store as a metadata column and a value column. That's just blobs of binary. Straightforward, simple, easy to utilize. One of the benefits here, though, is that you can leverage Parquet dictionary encoding. And so if each value in your has the same fields, then you can dictionary encode the metadata column and significantly reduce the size. Because the raw metadata, those metadata blobs, are going to be the same if the different values have the same fields, because the fields should always be stored in less graphical order, sorted. So the field names will always be the same if they have the same field names. So you can dictionary encode it. And then for the couple of rows where maybe they have extra fields or fewer fields, they stand out and you're not paying the same storage cost over and over and over and over for the same metadata case. So it optimizes that scenario where you have a column full of the same, where most of them are the same fields. It's simple to understand and also converts very easily to representation of Apache Arrow, which is the common way most things interact with Parquet is when they bring it into memory, it's in memory as Apache Arrow, and we added a canonical extension type to Arrow specifically to represent this and to give us that zero copy interoperability between Iceberg, Spark, all of them support Arrow, so Arrow can represent this data type with variant. So I mentioned shredding. Let's go back to that. What is shredding? What am I talking about? So variant shredding allows you to split any common fields of your variant into separate physical raw typed columns outside of the variant encoding, which can then get you some column oriented benefits. In an example here that you can see on the slide here, let's say we have an event column. We store it as a variant, but we know that every event object is going to have a timestamp named event_ts. And let's say that we know that our use case is going to frequently select just the timestamp or going to filter on the timestamp and so on. If we don't have the shredding, the physical operations that need to happen to do this is it's going to need to, for every row in your columns, it's going to have to read the metadata value and the value field. It's going to have to decode the variant for each row, which is non-trivial. And then it's going to have to find that event TS field in the variant binary blob. Remember I showed you there's, it has the object header followed by offsets, followed by a whole bunch of information. You have to decode that to get to that event TS field and finally return it as a timestamp. If we shred that event TS column, the event TS field, out into its own separate column, we can just read the column directly, the event TS column directly, and then return the column as is. There's no per row decoding necessary. We don't need to even touch the metadata we don't need to touch the metadata column at all, and so on. So in the scenarios where you have specific subfields that are going to be in most values, and that your use case is going to either select just that column or filter on that column, shredding makes a huge amount of performance benefit because you can avoid a whole bunch of extra encoding and decoding when you're writing and reading the data. It's not that complicated. You can see here we have the metadata field that we mentioned. You have the value we mentioned. When you shred a column, you add a typed value leaf column, and then under that typed value column, you make a group for each field that you are shredding. And each shredded field will contain a binary field, which is the remainder of the field after shredding that field out of it. Or maybe that's, if that row had a different type for that field. So for example, if for some reason one of the rows, the event TS field wasn't a timestamp and was a string instead, that would go into the value column of the event TS subfield so that you don't lose that information. To give a bit more explicit showing how this works, let's say if you look on the left side, you can see the object that we're going to encode as a variant. And the table shows you of the subfields on this slide, what actually goes into each of those subfields. And so for our expected case, you can see that the value is null because we fully shred it. Event type, event TS, we shredded both columns. We fully shred this thing. And so the typed value, the event type is null. The value is null because it is the correct type we wanted. And the actual value goes in the type value column. And then for the timestamps, you can see that we fully shred it. Now, in the second column, in the second row, you see that we have an extra field, a field that we did not shred. Well, you can see that the shredded fields get removed and added to their columns, but the remainder goes to the value column. And so at read time, if you're reading the entire variant value, you have to reconstruct the variant if you're not only reading one column. And that's kind of the important part of why shredding is not a thing you always do. You shred if you know that your use case is going to frequently be accessing, reading, or filtering on a specific subfield. If you are always reading or writing the entire variant, if you're never extracting individual subfields, you shouldn't shred that field, because at read time, you have to do extra work to reconstruct the variant. And I hope that makes sense, but if it didn't make sense, ask questions in the chat. And so just to kind of sum this all up, if you store JSON as a string in your database, your data engineers cry. In the case where your structure is stable, if you know you're not going to be dealing with, extra or missing fields, if you know that the field types will always be correct, just use a struct or a list column. But if the data types and the structure are going to vary, variant makes sense and is available now. Iceberg, Parquet, Arrow, whole 9 yards. But don't shred willy-nilly. Choosing which fields you shred or don't is an important thing to decide based on your query patterns. Don't just shred everything, because you're going to lose performance if you're never leveraging that. And that's it.